Now let us get a feel for poles and zeros a little further. Suppose you had 1 by 1 minus a z inverse. So, this of course is z by z minus a. We look at poles and zeros. This is something we already seen. Z equal to a is a pole. Z equal to 0 is a 0. Suppose you have 1 by z minus a, z minus b. So, the poles are z equal to a and b, all right. What about zeros? So, what is the definition of a 0? 0 is when the function goes to 0, all right. So, where will this go to 0? At z equal to infinity, all right. So, for very large values of z, this decays as, falls off as 1 over z squared. Therefore, z equal to infinity, there is a 0, and this is of second order. On the other hand, suppose you had z minus a by z minus b, z minus c in the denominator, then clearly z equal to b comma c are poles. You have a 0 at z equal to a, but then for extremely large values of z, numerator behaves as z, denominator behaves as z squared, and the ratio behaves as 1 over z. Therefore, you can think of this as having a 0 at z equal to infinity, and in this case the 0 is of first order. And once you see these examples, you can very quickly look at examples like this: z minus a times z minus b, right. Clearly z equal to a comma b are the zeros, whereas you have also pole here, and the poles are actually at infinity, and because this behaves like z squared for large z, you can think of this as a second order pole at infinity. And the other variants are just counterparts of this. So, here you have z equal to c is a pole in the finite plane. So, these are called finite plane poles or zeros, and you have zeros at z equal to a and b, and you also have a pole at infinity, and this is of first order. And in the general case, when you have b of z over a of z, then roots of a of z are the poles, and then roots of b of z are the zeros, and then you need to worry about whether there are poles or zeros at infinity. So, these are the finite plane poles and zeros. And we look at two special cases. Suppose you had a Z transform of this form, 1 plus A1 Z inverse plus A2 Z to the minus 2 up to AN Z to the minus n. If you want to talk about its poles and zeros, where are the poles, where are the zeros? So, this can be written as Z to the n plus A1 Z to the n minus 1 dot 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 up till AN divided by Z to the n. So, you have Z equal to 0, you have a pole, and this is of nth order, and you have zeros of this one, the numerator polynomial. Of course, here I am assuming there is no pole zero cancellation. If there were some zeros at Z equal to 0, some of those zeros will cancel with the poles at Z equal to 0. This is called an all zero filter. And this is called an all zero filter even though there are poles at Z equal to 0. This is because poles or zeros at Z equal to 0 are called trivial poles or trivial zeros. So, this is an important concept. So, poles or zeros at Z equal to 0 are called trivial poles or zeros, and later we will understand why this is called trivial. That is, zeros or poles at the origin are called trivial poles or zeros, because later when we look at magnitude response, we will see what role they play in contributing towards the magnitude response. Therefore, even though A of Z in this form has both poles and zeros, this is still called an all zero filter, because the only poles are trivial poles. And the counterpart to that, of course, is you have A of Z to be 1 by this same polynomial, and this is called as an all pole filter. This after all is the inverse of that. The zeros of the previous example become poles and vice versa. Even though there are zeros for this all pole filter, all those zeros are at Z equal to 0. Therefore, since all the zeros are trivial zeros, this is called an all pole filter. If you had both non-trivial zeros and non-trivial poles, that will be called as pole zero filter. Let us look at this particular example. So, this is h of n is 1 over n for this. Therefore, h of z is 1 over n 1 plus z inverse z to the minus 2 up to z to the n minus 1. This of course can be written as 1 over n. You can sum up this geometric series. So, this is 1 minus z to the minus n by 1 minus z inverse. Now, if you look at the poles and zeros of this transform, you can rewrite this as z to the n minus 1 by z to the n. Denominator also can be written as z minus 1 by z. Therefore, one of the powers of z will get cancelled. So, you will be left with z to the n minus 1, and then of course, you have this scale factor of 1 over n. Now, if you start to look at the poles and zeros of this, there is a pole at z equal to 1. There is also a trivial pole of order n minus 1. So, you have this. What about zeros? Zeros are the roots of the numerator. So, the numerator polynomial is z power n minus 1. Therefore, the roots are nth roots of unity. Okay. Therefore, if you now plot this, say for example, if I assume n equals 8, I will have 8 roots. So, I will have, let me plot the this is assuming n equal to 8. And if you look at this point, you have a pole at z equal to 1. You also have a 0 at z equal to 1. Therefore, what is happening here is pole zero cancellation. Therefore, in this form, you see that this is an all zero filter, because the only poles are the trivial poles. So, this is indeed an all zero filter. In this form, it seems to have both poles and zeros, but it so happens that the non-trivial pole at z equal to 1 gets cancelled by the non-trivial 0 at z equal to 1. Therefore, the only non-trivial pole that is there in this representation actually gets cancelled out. Therefore, there is no uncancelled non-trivial pole. And immediately you can also see why such a function that does not have uncancelled non-trivial poles has to be FIR. And the reason, it is very easy to see why this is the case. Suppose you had a pole here that is uncancelled, clearly this is non-trivial because this is not at z equal to 0. And for simplicity, I have shown the pole to be on the real axis. And suppose if the pole is at A, then if you look at the transform, in general we are considering ourselves only in the class of rational transfer functions, and you will see that 1 by 1 minus AZ inverse will be a factor in the transform. And if you do the inverse transform, then if you do partial fraction expansion, you will get k by 1 minus az inverse as one of the terms in the partial fraction expansion. And depending upon the region of convergence, whether the region of convergence is mod z less than a or mod z greater than a, the inverse transform corresponding to this will either be of the form k times a to the n u of n if the ROC is mod z greater than mod a, or it will have the form k times a to the n u of minus n minus 1 if the ROC is mod z less than mod a. So, given this factor, depending upon the region of convergence, the corresponding time domain will either be this or this, and these are infinite duration sequences. This is right sided infinite duration, this is left sided infinite duration. Therefore, if you have a pole that is non-trivial and that has not been cancelled out, when you do the inverse transform, it will give rise to a sequence that is an exponential that is either left sided or right sided. Therefore, that is why if you had an uncancelled non-trivial pole, this system will always be IIR. So, this kind of reminds us of that example. So, we will continue this and see the connection between the recursive implementation that we looked at last class and tie these two things together.